here another arrow to bring this guy up to the position of the previous one. And then again another x here, bring this down, x here, bring this.
Just to make sure, by adding x, you mean like acting with sigma x operator and these points
yes.
On the state?
Exactly.
Yeah.
Okay. And that's exactly what is encoded in this schematic representation. So I start about with these guys, but then I add these operations, and then I swap their positions. And what happens in this case is nothing happens because all of these edges anyways commute, so nothing can happen. So I'm back at where I started from. Because it's a loop, I can absorb it into the fact that I've anyways some of all possible loops. So this here, with this loop, is the same as the loop.
This is not the same as applying UR operators in some order, but then change the string, and there is no way to make this operation as a product of URs at some size.
Well, in the end, it is a product of URs. I think because ultimately, after the operation, now that I've done the operation, I've added a whole loop. And that is indeed it. So this here is this line appeared twice. So this line here appeared twice. So this came from here. Right? That's what it is. But of course, it appears twice means I've added this entire loop here. So effectively, bringing this around the other one is just applying 1 to x here, 1 to r here. And that's exactly the reason why nothing happens. So since QR is a 9, so I've only closed the loop. Okay, and I can play the same game with the E. For E's, do the same thing. E equals EE. Now the interesting bit, you have an E and an M. So we have an M here, there's an E that ends, let's say the E ends here on this side. And so this is an E, here we have an E, here we have an M. So we have an E, in this case is here, the M is over here. Now I cannot ask the question about exchanging that position, I can only ask the question what happens when I bring it around the other way. So the question is, of course, when I bring it around each other, I get something that is, well, more or less the same configuration as before, but I can have a quiet phase.
Sorry, I suppose I missed a little bit the point of exchanging M and M. So the conclusion?
The conclusion is they behave as if they were bosons. M with respect to M is like a boson.
Because we have a closed circle and that's one. Okay, okay.
And that's what this means. So in general, when you exchange two anions, of the same type, you can exchange their position, you can ask the question about it. And in general, if these are abelian anions, then you can acquire a phase. That would be the general notation. Right? And in this case, the phase is 1. So maybe that's confusing. You don't see really why I do this notation. This notation indicates that this theta is 0. Or M with M. I always forget where I left my eraser. Yep. Okay, so now we want to have this M particle and this E particle here. And we want to play a similar game. So we want to bring this M particle around the E particle. So what we do is, first step is, maybe we can go straight down here since we want to bring it around here. So first step here would be applying X here. Then I have to apply an X here, but mind you that there is already a Z. Because this is a string of Z's. An open string of Z's. So as I apply an X here, and I bring this thing across to act on my ground state, I will acquire a minus sign. So here I get a minus sign. really the place where we find. So I apply this guy across. Now I bring it across here. Now I go up. Now I go up again, and then I bring it here. But these are all in on-course. It's only this specific operation that is done. So whenever you have an M and an E, you bring the M around the E. So we have here situation of E that was down here somewhere. And here we get a minus sign because we have crossed one of these lines. So this is represented as follows. We have an E and M which does this, goes back to where it is coming from, and E which does this. E, this is the M. This is minus M. Let me see if this is the same thing that I used. Okay, it doesn't really matter that much, but I had used the reverse notation here. EM. Yeah. So the point is that in this model we have excitations above the ground state, and these excitations are the ends of open strings. And when you want to bring one of these open ends around another one, there's no way to avoid intersecting the other string. And in this intersection process, you apply a minus sign. Okay?
It should be like 2 times the language.
Yes. No, this is just a state. No. So here we do it. Okay, so that's what we call it differently than the theta there, because it's fine. Some phase fine, I don't mind. I'm just saying that when I do this operation, I come back to the same wave function up to a phase. That's just kind of thing. And now I tell you that the space that I get here is fine. This is weird statistics. So while these guys behave like bosons with respect to themselves, they have a weird mutual statistics. They're actually called mutual semions. Okay. So what you see is that we do have some weird angles in the theory. And we can also try to find out what the epsilon does. So I told you that we have, let's see if I can color code it a little bit. So the M was blue, the M was green, and the E was blue. Oh,
Or the E.
Yes, second. Yes, please. We have what?
So when we wrap it around, we can use the product over the sum or loops.
So what I'm drawing here is just a string. So when I draw just a single string, like this one, that's the operation that we do to create an excitation. What we had here, when we started, was essentially this excitation which ended up here, and the orange excitation which ended up down here. Let's say we had WM, WE ground state. Yeah? Next, I extend the WM in the fashion that I did here. This effectively corresponds to adding a loop to this WM here. This loop I'm dragging around across this WE. In this moment I get a minus sign. And then I let the loop act onto the ground state. Acting with a closed loop on the ground state gives you 1. Because the ground state is the sum of all loops, so it will just cycle.
So I understand ground state. So I also need when I have the equal I5, I also need the sum over.
So I see. So here, this notation here of a cat is I have applied this thing onto the sum of all loops. This notation is not. This is not just one string. This is the string plus all the possible.
But what does the pi circle that mean?
This here means the product of operations that I did here. sorry, this is a notation of just the product of operation. So if you want product of, in this case, this is product of moves. Okay, so now we discussed that there's also a possibility for this third particle, which is essentially bounded off EM. So how does that behave? So imagine we start, so what we want to know is, okay, we need to know all sorts of things, what's the statistics with the E, what's the statistics with the M. But the one which is the most interesting is to look at what happens when I start with an epsilon. These are indistinguishable particles, epsilon. So I can ask the question about changing its position. So I want to exchange the position of an epsilon. So what's an epsilon? An epsilon is a bounded of E and M. So it's this. That's what I want to do. This. Very good. Get with the right notation here. Well, we'll see. Maybe I can. So the first step is to see. Very good. The first step is to see that here we have something like I can extend this. Maybe I'm over pedantic, but let's extend this here as an intersection. So we have this guy coming here through. I'm drawing it like very pedantically. This guy here going like so. Yes. I've just added a little bit in this intersection part so that we see better what's happening next. The next thing that we're doing is we're using that E and M with respect to themselves are bosons, so I can straighten these lines. So what I can do is this line here, I can just do this at this point, and then the one which comes from here does this, right? So I will maybe first draw and then explain. Similarly, this guy does this. So what I've done is at this intersection here, I've connected this line to this line and this line to this line at no cost because anyways it goes on. And I've done the same thing here with this one and this one. This now goes left, this one goes here because there's no cost.
But we didn't discuss the statistic of ease themselves.
We did.
We did. Okay, sorry.
I just very quickly said the same thing.
Yes. Okay. Yes, sorry.
And now here you have this thing which is an M particle and an E particle, one going around the other. That's the one that gives you minus sign. So this particle gives you minus sign. So what you then get is minus. That means epsilons are fermions with respect to themselves. Yeah, well, M and E are bosons with respect to themselves. I mean, I put this in quotation marks because everything is an ennion and there's weird statistics with other things. But with respect to themselves, these behave like bosons and this behaves like a fermion. All right. So maybe it's worthwhile to highlight this. Yeah. So I think this is crazy. We started from a model which is really just qubits. And the excitations are point-like. There is a point-like excitation of qubits which behaves like a fermion. Is that weird? I think it's amazing. There's even like the idea that the electrons that are in our body are like this. In reality, we're all like in a big, we are in a big topological error correction code, and the electrons that are in our body are actually opposite. Of course, it requires to extend these ideas to dimensions, which, as I explained, is a little bit more tricky, because it's more complicated to get something real exchange statistics. Then there is also another, maybe an academic statement about superconductors. In a superconductor, the excitations that you have are, so first of all, a superconductor is not a symmetry-broken state, because if you take gauge symmetry seriously, there is no symmetry to break. Right? So instead we have like Anderson-Higgs, etc. In particular, a superconductor has, the Goldstone mode is eaten, there are no low energy modes in superconductor, just regular gap fermion spectrum. The excitations in a superconductor are Bogoliubov quasi-particles, so these are electron-hole linear combinations, which cost energy delta. And then the standard other excitation is a vortex. The vortex, of course, it's a vortex of the superconducting order parameter, so it has H over 2E. When you bring an electron around the vortex, since it's not a full flux for the electrons, it's only a full flux for the Cooper pairs, you get a minus sign. This is R14. So this is the same thing. I didn't show it explicitly, but you can also check here. When you bring such an epsilon around an M, well, essentially it's obvious. When you bring an epsilon around an M, the epsilon is composed of an E and an M. The M with the M doesn't do anything, but the E with the M gets a minus sign. So bringing an epsilon around an M gives you a minus sign, which is the same thing that happens in a superconductor, where you have fermions when you bring them around the vortex. That's the difference. So you can essentially interpret a superconductor, given that a superconductor doesn't have any spontaneous symmetry breaking. You can ask the question, what is this thing if it's not spontaneous symmetry proper? You can argue that this has a topological one. Maybe a bit pedantic, because I guess we can understand superconductors very well without having ever understood anything about topological order, but it's a way of doing it. Okay? And we can switch to the ground degeneracy on torus. So I mentioned in the introductory presentation to this course that topological order, intrinsic topological order, comes with a non-trivial ground state degeneracy if you have a closed manifold with a non-trivial genus. This is what we're going to see. But what I also mentioned is that this is related to the anyons in the sector, and this is also what we're going to see now. So we have already introduced the anyons, which in this case of the toric order is the E, the M, the epsilon into it. And you can actually see now how when you get the ground degeneracy essentially by playing with these strings. Ground degeneracy in a torus. Okay. So the basic idea is the following. We discussed that the ground state is given by a bunch of loops. But now I want to ask on a torus, I can have various types of loops. I can also have these types of loops. And is the ground state that contains an odd number of such loops the same as the ground state which does not contain such, which has just even number of such loops which wrap around one of the holes of the torus. So, okay, so yes, okay. So what we do is we apply first the magnetic holonomy. So that's so what we do is the torus is going to be represented as a plane with periodic boundary conditions. And what we want to build is the magnetic holonomy. So this is called x1 here. x1 is a product of all bonds. The horizontal, I will show you in a second how this looks like. Gamma horizontal of new axis. And so it would be ultimately what I want to do is, so this is periodic boundary conditions. I want to drive a string which goes just across the system, which is essentially what this guy does. So ultimately that's our x1. Okay, and the question is, so yeah, so it's x. X. Okay, question. Is x1 of the ground state some phase times the ground state? Same ground state? So with this ground state, I mean the one which is, let's say, well, we start with some ground state. And the answer to do this, we build a second one. We build a second holonomy. So this was the magnetic holonomy, also called Polyakov loop, magnetic holonomy. Or actually Wilson loop maybe. Wilson. Yes?
Or just holonomy?
Well, okay, so in this case it's just a word. Holonomy usually is one way to characterize topologies. People discuss multiple groups or groups. Here's just a word. Take it as a word to describe this. Actually, I never understood how this relates to different geometry. The same thing. If somebody knows. Okay. There is the electric one. Electric holonomy. And that, as compared to the Wilson loop, it's called Toft loop. Toft loop. And that's Z1 part over all B vertical. And then here we do the uses. B. And so that's of the type of data one. So let me just color code things again. This guy is for the Wilson loop. This guy is for the Toft loop. Z. So therefore, what we see immediately is that there is actually a two-dimensional Hilbert space. So both x1 and z1 commute with Hamiltonian. With H. That means energy is unchanged. Unchanged. So for any wave function psi, x1 on psi has the same energy as psi. If psi is the same. So definitely, if you start with a ground state and you apply either x1 or z1 on it, you still get a ground state. But also, x1 and z1 anti-commute, so you get a two-dimensional Hilbert space from them. In particular, so that means that your ground state, so far we are just a two-dimensional, you see before. If you take a ground state, so of these two ground states that you have, there are at least two ground states, you can take a linear combination such that the z1 is a linear combination which corresponds to an eigenstate to z1, then obviously x1 flips to the opposite eigenstate. So the other thing that I should maybe say, well, this depends. So they commute with it. The Hamiltonian energy is unchanged. Moreover, we also have z1 squared equals 1 and x1 squared equals 1. So they have eigenvalues plus or minus 1 again. So they just have a Clifford algebra, x1 and z1. Okay. So then the answer to this question is, depends on which ground state we had, but if we chose a ground state such as z1 on this ground state with extra label little z1, this z1, little z1 ground state with extra label little z1 is plus or minus 1. Then x1 on ground state little z1 is the ground state with minus little z1. I just flipped it. And actually you can build a second pair of such I need some space. You can build a second pair of holonomies. And thereby you get a second two-dimensional Hilbert space. So in total you get a four-dimensional Hilbert space. Maybe I draw this. We draw this with dash lines there. So this here was my x1, this here was my z1, and then we can take a horizontal line dashed here, which is my z2, and so this is the product of these, of course. And I can take a vertical line, also dashed here, of x's, x, and this guy we call x, and we get yet another two-dimensional Hilbert space. Yeah. And then moreover, you see that the z1 and the x2 commute. Even if you chose a different contour for the z1, it would go over the x2 twice, so they would also commute. Okay. So then there is another pair. Same with x2 and z2. Note, what did I say? x2 z1 equals 0. 0 is the same as Z2x1. So in total we have 40 Hilbert space, 40 fourfold ground symmetry.
Sorry?
Yeah, 1 second.
Huh?
On stage. Yes.
X2 probably should go to the centers of the squares, right?
Yes, that's
absolutely
absolutely
correct.
correct.
Thank you.
Yeah, thanks for paying attention and correcting if necessary.
You're welcome.
What I said is still true. If you have a Z2, if you take a Z1 which does this loop like so, it will intersect twice. And therefore they will also. Okay. Now maybe I can say something about a. Should I say this at this point? Yeah, maybe. Yes.
Matter that, well, it depends, that we have a deterministic with respect to row and column.
I didn't understand. What do you mean with degeneracy?
X and Z depend on the column.
Are you saying what if I took this guy?
Yeah.
Because maybe let's think about the green ones, because I always do green loops. It doesn't matter, because I'm always acting within this space where all the loops have been already taken into account. So anywhere is the same. Thank you, that's actually important. So therefore it's really only 4-dimensional, not more. And also you see now why I have been emphasizing that when I have been switching from my local qubits to the basis of B's and Q's, I've been saying that the number of degrees of freedom is nearly the same as the number of qubits. That's because of the boundary condition. So essentially you have these 4 extra things. So differently said, if you any of these 4 ground states still have all B's and all Q's equals +1, right? So just saying on the torus, saying all B's and all Q's are +1 is not sufficient to uniquely determine the ground state. It puts it into the right manifold, but it doesn't have it. Then there is maybe something a bit more modern that I wanted to say. And that's sort of something that I still have problems to philosophically understand. The whole point of this lecture course is to show you states of matter where you have quantum order beyond Landau without spontaneous breaking. What I'm saying next is the modern, it's very recent developments. People start to discuss topologically ordered phase as spontaneous breaking. And it's still true that there is no local order parameter, but it's discussed in the context of spontaneous symmetry breaking, but the symmetry that is broken is not a global symmetry, which is called zero-form symmetry. It's spontaneous breaking of a one-form symmetry. So people discuss the following. This is just on the side. So usually when you have a symmetry operation, let's say in the Ising chain, with an operation that I think I call Q, and it's just the product of all x's. I mean, I call it sigma x. And let's say for the original model, I have erased now. For the 2D model, I had degrees of freedom on this star lattice. And if I do all x's, that flips to sigma z, both sigma z's are flipped, it doesn't do anything. Of course, it comes to the Hamiltonian, the transverse field is in x direction anyways. That's called the global symmetry, or a zero-form symmetry. So it acts on the whole system at once. And when you have spontaneous symmetry breaking, you get 2 ground states in this case, because this is a Z2 symmetry. And what you have is you have ground states all up. And you act with Q on it, you get the other ground state, which is all down, right? So the ground states, of course, are separated by exponential. The extensive height tunnel barriers, so that the ground states in a magnet don't tunnel into each other. But in principle, there are two ground states, and the Q operator brings you from one to the other. Then there is something like one-form symmetries. And these are generally discussed quite extensively these days. And these are operations that don't act on the whole system, but only on a line. In the present case, we have effectively Z1, X1, Z2, and X2 as one-form symmetries. And of course, variance thereof. And variance thereof. Variance means other groups, yeah? So we have these loops which commute to the Hamiltonian. And yeah, I had to erase the Hamiltonian, but the Hamiltonian being a product of all, I told you that these x's and this commute to the Hamiltonian, right? So I also told you that these guys here are the ones that are cycling between the ground states. So effectively what you can think of is that once you're in a given ground state of a ferromagnet, you point all up. Yeah, that breaks the symmetry in the sense that the symmetry operator brings you to the other ground state. And very similarly, you can think about the deconfining phase, the logically ordered phase, as spontaneous symmetry breaking of this one form, which brings you from one ground state to the other. Now, what's atypical as compared to zero forms is that when you break the symmetry explicitly, you add a field in z direction, you will split these two ground states. And there's something general apparently about these higher form symmetries that local perturbations cannot split the various ground states. That's not only true for discrete symmetries. Here we have a higher form discrete symmetry, Z2 symmetry. But it's also true for higher form continuous symmetries, where the Goldstone modes cannot be gapped.
So this square represents a torus, right?
Well, the square represents something, just the system. Yeah.
Okay. Isn't it important that this loop goes around the torus? Because
so for the torus, to go from one to the other, to go from one to the other. What I want to say is that there are the loops, any loop is a symmetry. So, because any closed loop commutes all of the Q's and all of the B's. So that's a symmetry. Symmetry means an operation, some operator which commutes with the Hamiltonian. The ones which are cycling through the ground states are the ones which go across the boundaries. Yes. Okay, anyways, I wanted to just mention this on the side. These are new developments. Okay. The other thing that I wanted to mention is perturbations to the toric code and the Fresnel-Schenker phase diagram. Yeah.
I'm not quite sure why this is a fourth of the degeneracy with X before. So, because what if you apply the big X1 just one line higher and lower? I don't know if this was already said.
No, so what I was trying to say is, you have two pairs of polynomials, which, so the two pairs, the pairs commute. So, for example, x2 and z1 commutes, and z1 x2 commutes. Sorry, x2 z1 and z2 x1. They commute. So these are the pairs. So the one with index 1 and the one with index 2. They are both pairs. And these pairs, within each of these blocks where these pairs live, we have a Clifford algebra. So each of these sets, so you can, what I'm trying to say is you can block diagonalize a Hamiltonian to the sector of the ones and the sector of the twos. And then each block, that's the one where the x1 and the x1 and z1, for example, is here. This must be together too because they are anti-commute. Yeah, so the eigenstates, if you wish, you can choose the z1 and z2 bases. Then little z1 can be plus or minus 1, and little z2 can be plus or minus 1. That's 4. Yeah. Yeah.
Don't we also get degeneracy not only for the ground state, but also
Absolutely. Absolutely. But I was highlighting the ground state only because that's the part that is sort of most interesting, I think. Yeah. Maybe I should also say 2 more things about it. So first of all, the Tori code is discussed as a topological error correction code, and in particular, the Tori code itself can be used as a very stable means of encoding information, quantum information, where the physical qubits are those that live on these bonds, but the logical qubits are the ones, are these guys. So they're these guys. So that the space where you want to store your information is, for example, this one. So the eigenvectors, eigenstates of Z1. And now you understand, to undo this, that's what I said in the context of these higher form symmetries, to get out of the ground state, you have to do something non-local, right? So we are in this, let's say we have the eigenvalue Z1 equals plus 1. That's our, state that we want to, the quantum state that we want to store. Let's see if this information gets lost over time. In order to go from this one to another state of the ground state, so everything else goes standardly, right? You have to apply this x1, but the x1 is applying an extensive number of x states. So you need to have an error, not only here, but you need to have somehow a situation where a lot of errors sort of combine and happen at the same time, which is of course very unlikely. And that's sort of the idea why this is a good way to encode information in a stable. The other thing is, I didn't highlight this. This was the quantum information point. From the quantum spin liquid point, I didn't highlight this too much, but we had these loops where we have like these ups and downs. So on every side in the whole sequence, we have as many ups as you have downs because you have these loops all the time. So the magnetization on each side is 0. So there is no local order operator. There's spontaneous symmetry breaking only in the sense of this higher form symmetries, which are anyways non-local order operators. But I mean, I just want this higher form symmetry is just, I included it because people are discussing it. We're not saying that everything that was said before is wrong. It's just a new way of interpreting it. So still there is a lot of entanglement. Still it's stable. I forgot the number that we have here. 4.2.5 perturbations. Perturbations. So we had before the Hamiltonian as follows. So we had this Hamiltonian. Minus lambda, sum of all plaquettes, plaquette, minus h, sum of all positions, qr. That was the Tori code. We also had discussed briefly this as a perturbation, but then I dropped it, and now I have to return to it. Minus G, sum of all B, mu C. Now the system is not anymore integrable, and as I said before, the higher form symmetry is explicitly global. I mean, as soon as these J and G are not. Yet we have a gap, and a single such mu, as I just said, a single mu x is not enough to bring me from one ground state to the other. It will not be able to lift the degeneracy to ground states. The matrix elements only happen in L4 perturbation theory, where L is the system width. we can ask the question, what happens? So we had before this line. The phase diagram is typically drawn as the following. This is G over H, and this direction is lambda over G, lambda over J. This is reverse of what we drew before, but it's sort of the convention as you find it in many papers. So then, when H is infinity, that was our Z to H theory. So this line here Z to H solution. H.
May I ask a question?
Yes.
The fact that we cannot break the kind of kill the gap by a local perturbation is not the property of the ground state, but of the excited state. We've actually seen that elementary excitations are strings, and we cannot create such a string by a local perturbation. So that's a statement both about the ground state and the excitation.
It's probably true.
So it's unfair to say that we've just constructed a funny state.
Unfair to whom?
I don't know, to ourselves.
So yeah, yes and no. I think that so you're saying that to discuss stability, so they say the ground state is not everything.
Right.
Okay. Yeah, I think
I'm just saying that how can we actually see that there's a gap in this model? We actually just construct explicitly the excitations and say, look, they are gapped, and moreover, they don't have dynamics, so that's it. Now, here we add perturbations, and how do we understand that the gap is still there? We just say, okay, we can naively try and do perturbation theory, just can see that at any order that is finite and not extensive in system size, we cannot create even a single perturbation, because it requires applying a string of those.
so, when I apply mu x, imagine I apply mu x, which is the one that comes from this J time. What do? I create two M particles because I flip, when I apply mu x here, I flip this guy from up to down.
Yeah.
That creates two M particles.
Yes.
So, what energy do they have? In order to say which energy, I cannot just speak about the ground state.
Yes.
Because the ground state doesn't know what's the excitation energy. Absolutely, I'm with you. However, actually, there is something interesting about these topologically ordered phases. That the ground state has a lot of information also about the excitations. So, amongst others, you see that we have these ground state degeneracy on the torus, which is a consequence of the type of excitations that we have. And you can calculate, for example, the entanglement entropy. And the entanglement entropy has this sub-leading contribution, which is topological for the toric code, and for any topological order phase. And it knows about the quantum dimension of all of the anyons. So the ground state has information about the excitations, which is pretty weird. I find this very weird.
Maybe that's probably what I asked you in the first lecture. How do I know that there's some nice properties of excitations looking by only the topology of the ground state? Maybe that's what I asked. I'm going to say that there is some information there.
I'm saying that there is some information, and okay, I know that this is true, but it's not exactly obvious for me how to see it. Yeah. But in order to, if you want to do perturbation theory, you also need to know also what you put into the denominator, right? And to this end, you need to know the Hamiltonian. You need to know whether I take, in this case, lambda to be whatever, 100 electron volt or 100 giga electron volt. Okay. So as h goes to infinity, we are enforcing the Q constraint exactly, which we are back on our Z2 gauge theory. And I told you before, now the only thing is now it's reverse picture than before. So on this side is the deconfining phase. And here's the confining phase. This is the topological order. What happens when I crank up the J? So I go from lambda to infinity, I increase my J over here. Well, I originally had my excitations, my M particles. was my m particle, right? When I have a j, it gives, so m particle, this is the energy of an m particle. This is 0, and its energy was 2 lambda above the ground state. When I have a j, what it does, I add once with the j, it will let the m particle hop here. Right? So what it means is that my excitations are not anymore degenerate over the whole system size. Instead, they're forming a band of excitation and they're starting to disperse. Oh, that's not a very nice cosine. They're starting to disperse. And the width of this dispersion, maybe I draw it in black so you can see better. The width of this dispersion is going to be j. So once the width of the dispersion hits the energy around which there is a dispersion, which is 2 lambda, you would have the transition. That's why this is what I want. So you can think of this here as m particles condensed. They're bosons with respect to themselves. E particles are not present at h goes to infinity, so you can just think about bosons. Yeah?
What is on axis x?
I drew a dispersion relation, so.
Okay.
Okay. Now there is a dual thing to this. There's a dual thing to this. It's hard to see at this point, but over here you have essentially an easing theory. I will probably not have the time to show it. Here you have essentially two easing theory. But in the notion of the Topological, you should think of this as still being the deconfined phase. And here my E particles condense. My E particles are charged. So when you have a gauge theory and charged particles condense, we call this a Higgs phase. Higgs phase. When does this happen? Well, it's the same argument. An E particle costs energy to h. With the mu z, it starts to move around. The width of the dispersion is going to be given by g. So again, it's order 1. Yeah, here's order 1. And the whole phase diagram has been determined by Franklin and Schenker. It looks like so. This is the deconfining phase. And as I said, this is the Higgs. This is the confinement. And what they found out is that in the bulk, except for first order transition which terminates here, these two guys are connected. So Higgs and confined phase are the same in the bulk. How do we see this? We take large G and small lambda. Large G, small lambda, so essentially we take large G and large J. We can continuously tune between J winds or G winds because it just tells us which direction we're polarizing the system. In Z or in X direction. That's what this arrow does. The new addition of this higher form symmetry is just to claim that actually that's true in the bulk, but on the surface, this guy is actually an S15. Symmetry, here we said we have spontaneous symmetry breaking of the P form symmetry, the 1 form symmetry. Here this is restored. And in particular, this guy here is an S15 phase. And so then there's a boundary phase solution. I will not have time to go into this. I wanted to give you the newest view on this boundary phase solution. And this thing is first order. We have 15 minutes left. I would switch to coupling König tutorial. Other questions? The next chapter will be about Fermi surface reconstruction without symmetry breaking and the topological loophole to Luttinger's theorem. So I'll introduce a model that I'll solve, and then I'll discuss the Luttinger's theorem probably tomorrow. That means on Monday. So, and if we look at this theory code, and Fermi is hopping. Maybe I will now switch to a simpler notation. Okay, so we consider the toric code coupled to fermions. I switch to this quantum info notation, dropping the mu, just writing capital Z and capital X for the Pauli operators. We have a toric code here, and I wanted to highlight that there is going to be a difference at this point when we couple fermions to the long. Namely, that we don't only have the Q, which ultimately is something like the charge. It needs to know about the zero charge of the fermions, so it also knows about the parity of fermions on the given side. So before it was just the particles in the angular brackets, and now it also has the extra part. And this here is the usual P. So P is this. Q is this. That also knows about the fermionic parity here. Z, and fermions swap around, but in a way which is reminiscent of the gauge theory. Remember the path substitution. So we have here something like, maybe a horizontal link. Fermions swap like this: Z dagger, Z, Z. I do spinless fermions. So these guys, the Z and the X are not the spin of the fermion. They're just the gauge degree of freedom, which happens to be also represented by bodies. And what you see is that this Hamiltonian still has all P's and all Q's as integrals of motion. For the P's, it's obvious. So first of all, the P's and the Q's still commute, obviously, it's the same as before. The P also commutes with the fermionic term, because the fermions have only Z's in it, the P has only Z in it, of course everything commutes. Now the Q and the fermionic term also commute, because when you have a hopping term, it changes the parity on one of the sides. And bring this hopping term down here. The C dagger changes the fermionic parity. So when you commute this red operation across this orange one, the C operator changes the fermionic parity. But at the same time, the Z and the X anti-commute. So you get two minus signs again. And still all the P's and all the Q's are integrals of motion. So why are we doing this? This is a model which, well, first of all, is integrable, or close to integrable. And therefore we can learn something. But these models are studied as they appear in fractionalization approaches to strongly correlated electron problems. So you know that there is something like a mod insulator, and mod insulators means that the charge is localized in a covered model, like hopping on some lattice in some dimension with spinful fermions. Doesn't tell you anything about the spin, and in principle you can get some weird entangled states, you can get spin liquids, all sorts of things. The fact that the charge is localized does not necessarily mean that the spin borders or something else. So you can't get out of the strongly correlated electron problems, you can't get in a material, in principle at least, you can get topologically ordered states. And that's sort of ultimately the holy grail of all of this quantum material business. So one idea that we will actually encounter here on the loose concept is that the pseudogap phase in the cuprates, so the fact that in the cuprates, maybe I should show you the cuprate phase diagram of these ones. The cuprate phase diagram is temperature versus doping. Temperature versus doping. There's an antiferromagnet here. There's of course a superconductor, which is roughly here. Then so the superconductor, we know about the superconductor, of course, is water parameter, which is D wave. We don't know really how it appears. And one reason why we don't really understand it is the following. In the, so this is above the superconducting dome, there are very weird states of matter that appear. So there are, here is the regime of the pseudogap, where it appears as if the Fermi surface was too small to be consistent with Lagrange's theorem. Let me remind you of Lagrange's theorem. Lagrange's theorem tells you that the size of the Fermi surface, even in the presence of interactions, is given by the Fermi density alone. It doesn't tell you the shape of the Fermi surface, but it tells you that the volume that's enclosed is given by the density. It's obvious in the free case, but it's true also beyond that. So the pseudogap phase appears to violate that. In RPS, we get like very weird signatures. We see something which is only part of a Fermi surface anyways, and moreover, this part is too small. The Hall, if you measure the Hall conductance in the cuprates, well, you have to kill, you go to smaller temperatures and you kill superconductivity by a field. Then you see an interesting jump that occurs here, which essentially tells you that the mobile carriers change by 1 electron per unit cell close to this point here. So this suggests that somehow the Fermi surface suddenly jumps. Here it's too small, here it's too big. But there is no symmetry breaking across here. So this Lagrange's theorem assumes that, as I said, the Fermi surface, even in the presence of interactions, is just given by the density, under the assumption that no symmetry is broken. And here you would have a situation where the Fermi surface is too small, despite that symmetries are not broken. And then here you have what's called the strange metal. So you have linear T resistivity and so on, which is weird. I will not speak about this at all. If anybody speaks about SYK, that's what people have been playing with SYK. If guitar speaks about SYK. Okay, I'm going to give you, I'm not saying that I'm solving the pseudogap problem, but I'm giving you an idea of how topological order can give you two small Fermi surfaces, and it's still consistent with Lagrange's theorem. Okay? So, I think what I can do briefly is I can show you the ground state for this model, and anyways, I have 2 extra minutes because at some point I've given you 2 minutes. So the ground state of this problem can be solved in the same way as we solved the ground state of the toric problem. The only thing is that, of course, now the Hilbert space, not only the Hilbert space of these operators living on the bonds, but also of the fermions living on the sides. The ground state, we do it as we did before. We first solve the problem in the absence of the H term, forgetting about the fact that there is Q term. Anyways, the Q commutes with everything. So what we do is, first step is we choose the configuration of all of these Z's such that we make the B term happy. A very simple one would be this. So nothing new, you know this way. You may wonder what happens when you change the sign of lambda, and what happens when you have fermions, whether the fermions, don't they want maybe a different type of flux? And for the moment, let's just discuss the situation where lambda is much larger than W in positive. So this is the case, lambda much larger than W. This is sort of the trial part of the ground state, which makes this guy happy. Again, all of the b's are integrals of motion. The ground state, positive lambda, is b is 1. What happens to the fermions? So, any state that we write down has to be a combination of what happens in the toric code sector and what happens in the fermionic sector. Once you've chosen this configuration of all z being plus, we just have a free fermion hopping problem. Now we know how to solve that. So on a square lattice, if I draw, for example, the Brillouin zone, then we got it somehow how to draw it. Let's say I draw this the Brillouin zone. This is the Brillouin zone. Then my fermions, which were red, everything's red. The fermions form at half filling this Fermi surface. All that I want to say is that once I've picked a configuration of the z's, it's easy to solve the fermionic problem, just before reference form. And now once I've done with this, I project it. Okay. This is the ground state in the regime that I just said. Why did I say that this problem is only essentially integrable? So all the p's and all the q's are integrals of motion. And I can construct any state by essentially this procedure in which I first solve the problem at, this guy here for a given configuration of b's. Here all the b's are 1. Then I solve the fermionic problem for this particular configuration, and then I project. The problem is, to get all states of the problem, you would need to be able to solve the fermionic problem in the presence of a random configuration of fluxes, which is ultimately sort of an Anderson localization type problem. And I don't know how to solve this exactly. But I know that the ground state is going to be the one, at least when lambda is very large, then I know that the ground state is a homogeneous solution, and for homogeneous solutions I know how to solve the fermionic problem. So, okay. We will see on Monday. I will continue on Monday with this thing here. We will see that there is also, when the lambda is negative, we get a different ground state, we get a different configuration of the Fermi surface, and we will discuss the Lagrange's theorem. Questions?
So, do you assume that we also have like a purely fermionic part of Hamiltonian which corresponds to some tight binding?
So this is my fermionic part, but I don't have that's all that I have.
Okay.
So, but I don't have a term which is just C take C. That would break integrability. Because it doesn't commute with Q.
Yeah, okay, I see. Then where the Brillouin zone actually came from?
So what I did is I chose a configuration, forget about this one.
Yes.
I chose a particular gauge, name my medium setting. Then all of the z's are +1. That's what this arrow is.
Yep.
Now I have to just solve this problem. I do Fourier transform. I get 2 cosines, as usual. On the square lattice, I get 2 cosines. And what I'm drawing here is just if I'm at half filling, I have this.
Okay, thanks.
Maybe I missed why now the fact that Q actually contains -1 to the n fermions.
Why
it's trivial as far as solving the hopping problem is concerned, but then.
Is it a question where it comes from, or is it a question?
I do understand where it comes from. I don't understand how the procedure of just filling the Fermi surface works with this kind of term.
Okay. So your question is within this model. It's not the question where the model comes from.
Yes.
Okay. So you agree that still all the q's and all the b's are integrals of motion, right?
Yes.
So when I act with the b on the state, I give that it commutes with the Q's, I just get 1 everywhere. When I apply with the Q, of course I get 1 everywhere because of the projective. So far everything's good. I think your question is mostly about this one. Do you agree Q still squares the 1?
Yes, I don't understand why. Okay, I fixed. Let's say I take the Tory-Code state in this form, and for this particular form, I'm trying to solve the fermionic part.
Yes.
And I can see that for this particular state, Q behaves in a weird fashion. So, and it contains fermionic operators. So how do I?
So all that I'm saying is that I can act with the Hamiltonian onto this one, and I know that I get the correct answer. So how do I see this? One thing is I act with the B's, one thing is I act with the Q's. In both cases, I get 1 in any case. The maybe more non-trivial thing is I act with this part of the Hamiltonian onto this state. What do I get? When I act on it, this part here, the whole fermionic part of the Hamiltonian, commutes with the Q.
Yes.
So whether I act here or whether I act here doesn't matter.
Yes.
Once I act here, the Z, since it's an eigenset of all of the Z, all of Z becomes 1.
Okay.
And then I just have to act with the fermionic part on the rest of the Hilbert space.
Okay.
And that's just the standard fermionic part.
No more questions? Okay, then 15 minutes break.
See you on Monday.